Now that we understand the basic reasoning underlying statistical testing, and now that we know how to draw conclusions from our sample statistics, let's quantify them. Let's try to put a number of uncertainty on the conclusion that we draw from our sample statistic about our underlying population. And we got to the point that we compare the value of our specific sample statistic to the distribution of possible values if the null hypothesis is true. Remember, the null hypothesis is that there is nothing interesting going on with the underlying populations. If our value falls within the bulk of this histogram, then we indeed conclude that there is nothing going on with our underlying populations. If, on the other hand, our value lies at the tails of this histogram, then we conclude that our sample statistic indicates that there is something interesting going on with the underlying populations. But this, of course, raises the question now, where do we draw the line between accepting the null hypothesis in these cases and rejecting the null hypothesis in, for instance, this case? Now, this means that we have to look for a measure that indicates how extreme a value is compared to the overall distribution. Now, this might sound familiar. And indeed, in the chapter where we introduced percentiles, we looked at some very similar situation. There, we had to judge whether the GPA of a specific student was exceptional or not. And therefore, we had to figure out whether a GPA of 4.1 was an extreme value considering the entirety of the distribution. And thus, the problem was exactly the same. And therefore, the solution will also be very similar. Let's look at an example. Here, the value for our specific sample statistic lies at this point on our histogram. Now, to get a measure for how extreme this value is compared to the overall distribution, we can do the following. We can compute the percentage of data points of this entire distribution that is at least as extreme as this value. Now, in other words, this means computing the percentage of data points in this distribution that is at least as far away from the mean of our distribution, which is a center, as our specific value. Now, because we have a symmetrical distribution, this means that these are these values on the left of our line, because they are farther away from the center, but also when we mirror our line to the right-hand side, it will fall somewhere like here, then all of the values on the right of this imaginary line, because these values are all further away from the center of our histogram than our specific value, and thus we consider them to be at least as extreme. Now, this seems to be a case where percentiles will come in handy, and of course, this is the reason why this cumulative distribution function of the same data is plotted here, because here we can very easily spot the percentages that we are talking about. We see that our specific value, which is this one, comes out to be roughly at the 20th percentile. This means that all of the values lower than the 20th percentile are more extreme or more further away from the mean. But because we have a symmetrical curve, we also know that all of the values above the 80th percentile are also more extreme. And this means that we can very easily add up the percentages of all of the more extreme values. 20% lower and additional 20% at this side of the graph. So 20 plus 20 is 40. So in this specific case, we can say that only 40% of data points are more extreme than our specific sample. Now, 40% of data points is quite a lot. So this seems to be not as extreme enough to reject the null hypothesis. If we, however, look at a more extreme example, we see, for instance, here, then we see that our specific measure for the sample statistic falls well in the tails of our distribution. And to get a measure for its extremity, we look at all of the values that are more extreme. So the tiny amount of values to the right of this line, and because we have a symmetrical distribution, also the tiny amount of values at the right of this imaginary mirrored line. And the same can be seen on the cumulative distribution function. We see that our value, well, basically is at the maybe at the first or at the halved percentile. And also then here we take half a percentile. And therefore, for this case, we can roughly say that for this specific value, the percentage of data points in this distribution that is more extreme than this value that we found is less than 1%. And this of course encapsulates the fact that the value that we found for our specific sample dataset is a very extreme value, and we can reject the null hypothesis with a lot of certainty. And therefore, to repeat myself, but it's important enough to do so, such an extreme value for our sample statistic indicates that there is indeed something very interesting going on in the underlying populations. And thus we found a suitable measure to quantify the extremeness of the data points compared to this overall distribution, which represents the null hypothesis. And of course, in a very typical fashion, this is how we get in a natural way to the p-value, because what we just described is exactly what the p-value represents. The p-value is the percentage of data that is at least as extreme as the observed data point, given the null hypothesis, of course. Or said differently, the p-value is a measure for how unlikely an observation is given the null hypothesis. Going back, we could then say that the p-value in this case is less than 1%, and in this case we found it to be roughly 40%. Now, if this is still a bit confusing, let's just look at some simulations and some visualizations to make things clear. The figures in the next couple of slides will bring everything together. Now, if some of these figures are not clear to you, don't worry, we will come back to them in detail once we dive into the code and generate them ourselves and play around with the parameters. So in the top left, we see the histograms of the population datasets, which of course are in practice not available to us. But from them, we can see that there is indeed a crucial difference between the means of these populations. Then on the right of that, we see the histogram of two samples, each drawn from its corresponding population. If we compute the mean for each sample, which is represented by this vertical line, we see that there is indeed a difference in sample means. However, just by looking at this histogram, you wouldn't want to make any conclusive statements about whether the difference in means of these samples indeed translate to a difference in means of the underlying populations. However, we know now that if we take the difference of these means as a value and we plot it onto the histogram representing the distribution under the null hypothesis, meaning that there is no difference between these two populations, then we can make some conclusive statements. In this case, for instance, the difference between these two sample means is indeed an extreme value on this histogram, which can also be seen in the cumulative distribution function. More concretely, we computed a p-value for this value, which we will learn how to do shortly, to be 0.005, meaning that only 0.5% of values of this entire distribution are more extreme than the value that we got from our specific sample. So this means that we can reject the null hypothesis, and therefore we can conclude that the magnitude of the difference that we found of these means in our samples is indeed indicative of a difference in means of the underlying populations. Now, of course, we're still working within the framework of statistics, and therefore every conclusion that we make is still probabilistic, or in normal words, we might make the wrong conclusions given our statistics, even though we did everything right. And to showcase this, let's look at this example. We again have the same populations with the same difference in mean, but now we have drawn two samples, one for each population, and the difference in mean of these two samples is so small that if we compare it to the overall distribution that represents the null hypothesis, that we do not get an extreme value. In fact, if we compute the p-value, then in total 35% of values are more extreme than our specific sample difference. And this 35% can be roughly verified on the cumulative distribution function, because we see that we have 17% on the bottom side, and because we have a symmetrical distribution, this would also mean 17% on the top side, so roughly 35%. So even though we did all of our statistics correct and we did not make any mistakes, we still come to the wrong conclusion based off our samples. But this of course comes back to the difference between representative samples and unrepresentative samples. And sometimes you're just unlucky. In this case, we've gotten an unrepresentative sample because the means of these specific samples are so close to each other. But that's just a fact of life for data scientists working with statistics. In this case, we concluded that there is no difference in our populations judging by our samples. But these faulty conclusions can also go the other way around. In this scenario, we start from two populations with the same exact mean. And then we draw two samples, one for each population, and compute its average. These are represented by these vertical lines, and clearly they are different from each other. But that is not really so surprising, because it would be surprising if we would randomly draw 15 data points for each population and compute their mean, and that these means would be exactly identical. We in fact really expect to have a different mean for both of these samples. However, we see that if we compute the difference between these means, that the difference is so large that it in fact falls within the tail of this distribution, representing the null hypothesis. So even though the null hypothesis is correct, meaning that the two populations are identical, we still got two samples for which the difference between the sample means is so large that it falls within the tails of the corresponding null hypothesis distribution. In fact, if we compute the p-value for our observation in mean difference for our specific sample, then we get 0.03 or 3%, meaning that only 3% of data is more extreme than the value that we found. And thus, we are right, in a sense, to reject the null hypothesis, because 3% is quite low. But in this case, we falsely reject the null hypothesis, just because we got unlucky with the drawing of our samples, not because we did any wrong statistics. And this is important to appreciate. In statistics, it is not about being right all of the time. That's simply impossible. It does, however, give you a framework that allows you to draw the right conclusions most of the times. For instance, in the last example, we see that we again have these same populations with an equal mean. We draw two samples, one for each population, and we again see a difference in sample means. However, this time, this difference is small enough such that it falls within the bulk of the distribution representing the null hypothesis. And therefore, we cannot reject the null hypothesis because we don't observe any extreme value, and thus we accept the null hypothesis. In this case, we have a p-value of 54%, and thus we can confidently accept the null hypothesis. So therefore, starting from our sample data, which is the only data that is available to us, and we do find a difference in mean, we still cannot conclude that this difference will be there in the underlying populations. And this is the strength of statistics. And this gives you an insight in the power of the p-value. Even though we observe a difference in our sample, computing the p-value does not allow us to extrapolate this difference of our samples to the difference in populations. And to finish off this lesson, let's go back to the question, how extreme is extreme enough? Because now we've put a number on this extremity, namely the p-value, but what actual value of this p-value will be exactly our boundary between rejecting the null hypothesis and accepting it? Well, this brings us to our last concept, namely statistical significance. The statistical significance is basically a cutoff value for the p-value. It is your decision on where you want the boundary to be between accepting the null hypothesis or rejecting the null hypothesis. And this is indeed a decision, because in different fields there are different values for statistical significance. It all boils down to how certain you want to be that the conclusions that you draw from your data are indeed correct, or inversely, how much you want to avoid making the wrong conclusions from your dataset in the way that we saw in the previous slides. In most applications, For instance, in the psychological or medical literature, a p-value of 0.05 is considered significant. So in these fields, any insights that come from these sample sets with a p-value lower than 5% are considered statistically significant and thus are extrapolated to the entire population. In particle physics, however, they are much more strict. There, a conclusion is only considered statistically significant if it has a p-value that is smaller than 5 sigma, or as we saw before, smaller than 0.000004. For instance, the discovery of the Higgs boson was only published once they got to 5 sigma. Let's now talk about some consequences of taking the p-value as a measure for statistical significance. The first one is that the significant part of this word is about the statistics and not about the value itself. For instance, you could read a headline stating significant difference found in IQ between rich and poor. Now, this significant part will not be about the actual value of the difference or the magnitude of this difference. It does not mean that there is, for instance, a large difference of, let's say, 30 IQ points. Instead, this word significance in the headline is about the statistics, namely that this conclusion, which is drawn from a sample dataset, has a statistical significance, for instance, a p-value of 0.05 or 5%. In fact, the actual value of the difference in IQ points might only be very small, let's say 1 IQ point. Still, this difference of 1 IQ point can be called statistically significant. But of course, it's a very misleading headline, so beware of that. The second consequence is that if you take a p-value of, let's say, 5% or 0.05 as being the boundary of being statistically significant, so the boundary of extrapolating your conclusions from a sample dataset to the entire population, is that you will be wrong in 5% of the times. And this can be quite dramatic. Let's say, for instance, that in the psychological literature, all of the discoveries have a p-value of 0.05, then at least 5% of all these discoveries are actually wrong conclusions extrapolated to the entire population. So this is also something to really keep in mind. And the best thing to do, of course, is to increase your bar of statistical significance, as the particle physicists did. Now, before we dive into the code and generate all of these figures ourselves, and thus be able to play around with the parameters and get a better intuitive understanding of all of these concepts, let's first briefly recap what we have. First of all, you have only one sample, and thus only one sample statistic. Second of all, you have a corresponding distribution which is valid under the null hypothesis, meaning that there is no difference in population statistic. Then the third step is that you look at where your sample statistic falls in this distribution under the null hypothesis. If it is an extreme value, then you reject the null hypothesis, and if it is somewhere in the middle, then you accept this null hypothesis. And the boundary will be the p-value indicating your statistical significance. Now, in Python code, it is very easy to compute the p-value. In fact, it can be done in just one line of code. And then if you have a p-value, for instance, smaller than 0.05, you reject the null hypothesis. And if you have a p-value larger than 0.05, then you accept the null hypothesis. And it is in this way that using Python code, statistical testing is very straightforward. You just have to look at one number. But there are just too many data scientists and other professionals that don't know the underlying reasoning and mechanisms of statistical testing. But fortunately, you are now not one of them, because at this point, you really understand what's going on under the hood. So let's dive into the code and get even a more intuitive understanding.